Alright guys, welcome back. This is Unit 3, Lesson 3, and this is on the t-distribution and the t-test. So, let's start off with some definitions. First off, the t-distribution, and this is the big thing that this lesson is going to cover, and it has the similar bell shape as the normal distribution has, but the tails are thicker and the middle is thinner. So degrees of freedom are the only thing that can change the shape, and the degrees of freedom equal n minus 1. And now if you remember, n is our sample size, and so if you had a sample size of 18, your degrees of freedom would be 17, and it's as simple as that. So if you can see, this is our graph. This is a graph to compare the t-distribution at different degrees of freedom. And so our green graph there would be the t-distribution for degrees of freedom of 3. And if you can see, there's a lot of area on the sides here. There's a lot of area under these tails, so the tails are thicker. And so then the red graph would be t-distribution for degrees of freedom of 18. So this is getting closer to our actual normal graph, and then this blue Z would be our normal graph, and so you can see that this is as high as it gets, and then the tails are way thinner than the red or the green. And so normally, and if you remember our formula for CLT, which was greater than 30 sample size equals normal distribution, and so when we have a sample size of less than 30, that's usually when we're using the t-distribution, and then obviously you figure out your degrees of freedom from that. So 16 is lower and upper bound confidence intervals, and if you remember, we've done two-sided confidence intervals, but we haven't done a lower or an upper bound confidence interval. And this left one here is our 90% lower bound confidence interval, so that basically just means you draw your boundary at the bottom, and then 90% of the data is above that. And for the right one, it was 90% upper bound, and you draw your boundary on the right side of the mean, and then 90% of the data is to the left or below that. And so our last definition for this is reject the null hypothesis. And so when the p-value, and we'll learn about p-value later in this lesson, so when the p-value is less than alpha, and we reject the null to show that the alternative is true at our significance level. And we haven't heard of p-value or alpha yet, but we will get to that as we work through these problems. So you just need to know that reject the null shows that the alternative is true. And then if we fail to reject the null, that means we're assuming that the null is true. Okay, let's get into it. These are going to be longer problems. So this first one says, suppose that measurements of your systolic blood pressure are normally distributed with some unknown mean mu and the known standard deviation of sigma equals 7.8. You suspect that your average systolic blood pressure is high, so that would be mu is greater than 140. What is the most appropriate alternative hypothesis to support your suspicion with a hypothesis test? So remember, our HA is our alternative hypothesis, and that is the same thing. And so remember, this is like what we think is happening. And so since it says you suspect that your blood pressure is high, so that means mu is greater than 140. So that's just going to be our alternative hypothesis would be mu is greater than 140. So that one's pretty straightforward. The next part says, in order to perform this test, you are taking n equals 9 independent measurements over several days. And so now this 9 is less than or equal to 30, right? And so that means we can't use CLT here. So that does not work. And so this is why we're going to be using t-distribution on this problem. So the sample mean x bar is 144. Your test statistic is the standardized sample mean x bar. That is z equals x bar minus 140 over sigma over root n. So now we need to go up here, and remember it told us our sigma, so sigma equals 7.8, and that's our standard deviation. Sigma equals 7.8. And so what we would do here is we would just plug all this into the formula. So z equals x bar 144 minus 140 over 7.8 over square root of 9. And this is going to be equal to 1.5385. So that's our value of our test statistic, and that would go right there. And then so the part C says the p-value for the appropriate test in A is the area under the standard normal distribution to the right of the observed test statistic. So p-value, which is what we were going to define earlier, is the area under it that would be not included in the trial. So to the right of this, yeah, that's our p-value here. So I'm just going to set up a quick little normal graph here, or I guess it's a t-graph for this problem. So what we would do here is we would look and say, so 1.5385 is going to be right about here, and then here's our middle, so here's our mu, and then it's going to be 1.5385. And so we're not going to be able to do this by hand. We're going to have to use RStudio for this. And so our RStudio command would be pt, so pt of 1.5385. And then we're going to have to do, and then the next thing you do is rewrite the degrees of freedom. And so our degrees of freedom here, df equals 9 minus 1, right? Because n equals 9, so this equals 8. So what we're going to do here is write 8. And then since RStudio would give you all of this way, we want this way, we want to the right, so we'd have to do 1 minus this in order to get this part. Does that make sense? Okay. So this equals 0.062, and so that's our p-value. And remember our definition about rejecting the null hypothesis at a significance level of alpha equals 0.05. And so, alpha equals 0.05 means what this means is 95% confidence interval. So conf interval. And that basically you can find your alpha by saying 1 minus your confidence interval, so it would be 0.95 here equals 0.05, and so this equals alpha. And so should we reject our null at the significance level? And so our p-value equals 0.062, and this is greater than alpha, which equals 0.05, and so this means we fail to reject. And that's just based off our definition, because the p-value basically tells you how likely that your observation is of happening. And since our significance level is 0.05 and our p-value is 0.062, that means we have about a 6% chance of that happening, and we want less than a 5% chance of it happening in order to reject the null. So E says, draw the appropriate conclusion at significance level alpha equals 0.05. And so this would basically be your blood pressure is significantly higher than 140, or it would be is not significantly higher than 140. And for it to be significantly higher than 140, we would need to reject the null. So this would be is not, and the reason is because we fail to reject the null. Fail to reject the null. Okay. Cool. Good for that problem. All right, so this next problem is going to be we're going to have to use RStudio a little bit for this one too. And so what we're going to do, it says, what is the lifespan of a lab mouse? You measured the following lifespans for certain standard inbred laboratory strain, and you may assume for the following questions that the distribution of lifespan is normal. So we need to calculate the sample mean of these 5 data points. And the easiest way to do this in RStudio is to make your own variable. So I'm just going to call this x, and then you would do a less than symbol, a dash, and a c, open parentheses, and then you would write these data points down. So it'd be 813, 1125, 1074, 1025, and 759. So that's going to tell RStudio like what your it's going to tell you what your values are. So basically we just defined a variable with 5 different values, and now the easiest part of this is that in part A we can just say mean of x, and this will give us our correct answer. And so what this gives us is 959.2. And then for part B, all we would do is SD and then x again. So that's the easiest way to calculate our standard deviation. And so that's going to give us 163.14. So now we need to calculate the critical value t star for a 87% two-sided confidence interval. And so on this one, I'm just going to draw us another t distribution graph. So here's our middle, and then we want an 87% two-sided confidence interval. So that means we're going to have to draw 2 lines here where we have 87% of the data between those two. That doesn't really look like an 8. So we need 87% of the data between those two lines. And that means we're going to have how much to the left part of this. So in order to give RStudio the right number to get one of these values, we have to find out how much data is to the left of one observation. So what we would do here is we would do 1 minus 0.87, right, to get both of the tails, right? So this is equal to 0.13, and then since we only want one of the tails, we would do 0.13 divided by 2, and this gives us 0.065. So that's how much is right here. And so now the command in RStudio would be qt of 0.065, and then our degrees of freedom here, which would be what? So we have 5 total observations, so degrees of freedom equals 5 minus 1 equals 4. So we would do 4 right here, and this would give us our answer for this part of the problem. And so this gives us 1.9, and that means that at negative 1.9 here, negative 1.9 and 1.9, those are the amount of standard deviations away that our variable is going to be here. So now we need to calculate the margin of error for an 87% two-sided confidence interval. So the first thing to do on this one, right, remember margin of error, ME equals our T star for this one multiplied by S over root N. So what we would do is we would say 1.9 multiplied by our S, which is 163.14, and then it's over the square root of 5. And this equals, for this problem, 138.73. All right, so part E says the lower bound of the 87% confidence interval is this, and the upper bound is this. So now we need to calculate the upper and lower bound. So all we need to do for this is the lower bound would be X bar minus M, and then the upper bound would be X bar plus M. And so these are going to equal, the X bar minus M would be the lower bound, and this is 820.47, and then the upper bound is going to be 1097.93. All right, so that's it for that problem. Okay, next problem is you are interested in the weight gain of the Auburn freshman. You think that the average weight gain of the Auburn freshman student is not 15 pounds. You collect a random sample of measurements. The weight gains are a negative value indicates a weight loss. So these are our all of our observations, and so let's count how many there are. There's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18. So n equals 18, and what we remember about our degrees of freedom equals n minus 1, so that would be 17. So now we need to find our null hypothesis and our alternative hypothesis. So for this problem, let's see, the null hypothesis would be, so this would be mu equals 15, right? Because the norm, or what's usually thought of as happening, is that your weight gain is 15 pounds. So mu equals 15, and then we're testing to see if it's not 15 pounds. So this would be mu doesn't equal 15. So when you see a not equal to, that means it's a two-sided test. So two-sided confidence interval. Oh, that looks ugly. So this is a two-sided confidence interval. And so now the next thing we have to do is calculate the test statistic, right? And so what we would do for this is just like this problem back here is where we would tell RStudio a variable. So the first thing we would do is we would say X, just a random variable in RStudio, and then we would do the less than sign dash C, open parentheses, and then we would type in all of these measurements up here all the way through. So it'd be 16, 11, and then I'm not going to write some of them, and then I'm going to go ahead and say 15 and 7 at the end. But that would be, you would normally type in all the values, and then in order to get that's how we would find the mean. And so X bar equals mean, X bar equals the mean of our variable in RStudio, and then our mu naught, so mu naught equals 15, because that was up here. That's just our basic mean for the problem. And then let's see, we would need to find our S. So S equals S standard deviation of our variable. And then our N, we've already said, equals 18. So then the only thing left to do for calculate the test statistic is plug all this stuff in, and the mean is 12.611, and then our mu naught is 15 over the standard deviation, which is 3.2565 over square root of 18. And this all comes out to negative 3.1123. There you go. That's that problem. So then these last three problems are just testing to see if you know what to do with a hypothesis and how to reject a hypothesis. So what it gives us here is the significance level. So this first one, so this means, right, alpha equals 0.05. This means 95% confidence interval. And that's sort of the way I like to think about it. So what it says is, let's see. So what is it asking? Okay, so it's determine or decide whether or not to reject the null. So what it gives us here is our test statistic equals negative 4.2, and our alternative hypothesis is mu is greater than 3. So what we're actually looking for would be greater than. In a graph, we want greater than, and this gives us a negative t-value, which means it's way less than 3. So we would fail to reject, because if we reject the null, that means we're saying the alternative is true, and since we're going to say the alternative is false, we would fail to reject, right? And because we want a greater value, but since our t-value or our test statistic is negative, that means the value is less than. Okay, decide whether or not to reject the null hypothesis in favor of the alternative hypothesis at significance level 0.05. And remember, this means 95% conf interval. So now it gives us alternative is mu is greater than 3. And so this is saying our test statistic is 0.9. And that's basically saying we are 0.9 standard deviations away from the middle, so that'd be about right there. And to get at the confidence interval of 95%, that means we need to be 2 standard deviations away. And since this is only 0.9, we would need to be closer to over here in order to reject. That's to reject. And since we're not far enough, we are going to still fail to reject, because we didn't get far enough away from the actual value to be able to say, yes, it's a significant difference. So for the last one, suppose that a lower bound 98% confidence interval consists of all values greater than 4.5. Can you reject mu is less than or equal to 4 in favor of mu is greater than 4 at significance level of 0.02? So the interval already is 4.5 to infinity. So that's our confidence interval, and since this is greater than 4, so 4 is over here, and this is less than anything in that interval, we can go ahead and say, yes, we reject the null, because it doesn't matter what our significance level is here, because they're just telling us how they made the confidence interval. And so that's basically it for that one, is basically just saying our value that we're looking for is greater than 4, because the confidence interval has values. Every value in the confidence interval is greater than 4, so that means that we have to reject the null. So does that make sense? Good. Perfect. That's all I've got for you for this one. Thanks for watching, and I will see you in the last video very soon.